So hello everyone, today we're going to be talking a bit about stateless decoder virtualization through Virtio video and VA API, and this talk is going to be a tour on how this can be used in production on Chrome OS. So without further ado, my name is Daniel Almeida. I'm a consultant software engineer at Collabora, and let's get started. So by 2022, 82% of consumer internet traffic will be video, and this is according to a recent research done by Cisco. And in 2021, Android app usage on Chromebooks increased by a total of 50%, according to some data recently released by Google. And it turns out that Virtio Video is powering this today, which makes Virtio Video something you should really care about. But before we can actually talk a bit about how Virtio Video is behind all of this, we really have to talk a little bit about codec devices, and in particular about the differences between stateful versus stateless codec devices. So here in this picture you can see a decoder, a memory-to-memory codec device, and you can see that this decoder will operate in between two queues. On the left-hand side here we have the output queue, which is where one will be queuing bitstream buffers, and on the right hand side we have the capture queue, which is where one will be placing decoded frame buffers, and then the codec will be placing the decoded frames into these buffers as soon as it processes the data. And the idea is that this operation is going to be a loop where a client program will be queuing buffers on the left and on the right hand side, and eventually the codec will be placing decoded frames on the capture queue, and you'll be able to dequeue these buffers on user space. And there's no relationship in particular between queuing one bitstream buffer and getting one decoded frame. This is codec specifically. Codec specific. So, and the way that a codec works is by ascribing to what we call a finite state machine. And one might ask, why is there a finite state machine at all? Well, the reason is because before you can be in the all-important decoding state, which is where you want to be because that's where the data is going to be decoded, there are other steps that you must go through first. In particular, the initialization step is very important because that's where you're going to establish and negotiate what kind of media is going to be streamed through the codec device. But not only that, like what happens after you reach the end of the stream? Well, there's something called a drain sequence that also has to take place. So it becomes apparent that before you can be in this decoding state, you have to go through some other states first, and all these states, they're coded and encapsulated in this finite state machine. And lastly, we have to talk about the differences between a stateful and a stateless device. And the main difference for me is who gets to keep track of the decoding state. So for a stateful device, you can see here in this block diagram that the driver/firmware will be the piece that's going to be responsible for keeping track of the decoding state. And by decoding state, I mean the set of reference frames and some parsing state that must be kept between frames, and any other state that's necessary in order to decode data. So again, just to summarize, for a stateful device, the driver and the firmware will be the pieces that will be keeping track of the state, whereas for a stateless codec, this responsibility is shifted onto the user space client program. So in a stateful device, you can actually think about it as a black box where you're going to be submitting data and you're going to be retrieving some decoded frames back somehow. But in a stateless device, actually the user space client program will be taking on more responsibility, the responsibility for parsing the data and for keeping track of the decoding state. And with that said, now we have to talk a little bit about ArcVM. So ArcVM is Android on Crosvm on Chrome OS, which means running Android applications on Chrome OS with seamless, safe integration without switching to developer mode. And this is something that is already used in production for some high-end Intel Chromebooks. And in particular, this means that you can run any kind of third-party Android application, especially or in particular for the purposes of this presentation. You can run video apps such as the Netflix app, YouTube, or anything really that has to do with video on a Chromebook with near-native video decoding speeds thanks to Virtio Video today. And once we say this, I guess the next natural question is how does this happen? And now, in order to understand how this happens, we have to talk about Virtio and then about Virtio Video in particular. So Virtio is a family of virtual devices that look like physical devices to the guest, and they use the same standard discovery mechanisms. So the guest is unaware that it's dealing with virtualized hardware at all. It just sees a normal device. And usually the implementations, they're divided into two halves. So a driver will be implementing the guest interface, whereas the device will be implementing the host interface. So we're going to be talking a lot about this. So again, driver implements the guest interface, and this driver part is usually some kernel module on the guest's operating system, and the device is usually implemented in the virtual machine manager. So Virtio is a standard way, one standard, to achieve what we call para-virtualization. So in para-virtualization, the guest knows it's being virtualized, and by virtue of knowing that it's being virtualized, it can make guest to hypervisor transitions more efficient. And this massively improves throughput, because the alternative is when the guest doesn't know that it's being virtualized, the alternative is to have the virtual machine manager emulate a device. And in this case, a vCPU might try to access some device, say, using MMIO memory, MMIO, memory mapped IO, and when this happens, the vCPU will not be able to do this, and it'll have to transition back into the virtual machine manager by means of a very costly VM-exit instruction. And whereas when you're using para-virtualization, such as when you're using the Virtio standard, instead of doing this, what you're going to be doing is you're going to be communicating by sharing buffers. And this is going to be much faster because the host will have access to the guest's memory most of the time. So this is going to be much faster, and you'll be able to batch requests, which also will massively improve throughput. But this will happen at the cost of extra code, because when you're using a Virtio device, for instance, you have to actually have a kernel driver for this Virtio device and also a corresponding virtual machine manager implementation. So again, the idea is that you get massively improved throughput, but at the cost of a little bit of extra code. And with that said, we can talk a little bit about the Virtio workflow. So there's a lengthy initialization step that we don't really have to get into for the purposes of this presentation, but know that that's very important. There's some sort of a negotiation mechanism. There are feature bits which enable driver and device to negotiate on what kind of features they both mutually support. But really the most important thing we want to talk about here is this bulk data transferred through vert queues. So in a way, vert queues, they're the bread and butter of the protocol. This is where the driver, for instance, assuming a driver to device orientation, because it might be reversed, but assuming that we will have a queue where the driver will be making requests available, then the device will be given a chance to process these requests asynchronously without having to stop everything. So in this fashion, the driver will add a use buffer to the queue, and the device will be able to process this buffer asynchronously. It will possibly put back a response into this buffer, and it'll place the buffer back into the queue, and the driver will then notice that there's a response into that processed buffer. It will be given a chance to extract that response and possibly translate this response somehow, or even relay this response back to user space. So the idea is that these last two steps are repeated on a loop, and until there's no more data to transfer. And when there's no more data to transfer, there will be a teardown step. And each and every Virtio protocol or Virtio device will be able to choose on the number of virtues and on the semantics of the virtues used. So like this is like Virtio in general, but what about Virtio video in particular? So Virtio video, it supports 4 encoders and decoders using the same protocol. There's no separate Virtio video decoder protocol, and there's no separate Virtio video encoder protocol. But even though they're separate devices, they're supported under the same umbrella using Virtio video. And the protocol was proposed in the upstream mailing list. So the latest submission is RFCV5. And there's a Virtio video kernel driver, which was worked on by a company called Open Synergy, and the latest submission targets Virtio video v3, the v3 upstream submission. And the original versions, they were developed separately by Google and Open Synergy. And when Google sent v1 upstream, they noticed that they were basically working on the same protocol, so the work got merged, and as of v3, there's only one Virtio video protocol being developed. And in the Virtio video protocol, we have two vert queues. One being the command queue, which is where the driver will be placing requests to be fulfilled by the device, and the event queue, which is how a device will be able to asynchronously send events to the driver. And the key idea behind the Virtio video protocol is that the protocol can be used to implement the Virtio stateful finite state machine. So, and the way that it's going to do this is by presenting a stateful Virtio interface to the guest client user space, and then translating the incoming guest user space ioctls into the appropriate Virtio video commands. Then the Virtio video kernel driver will be placing these commands into the command queue, and the device will be given a chance to process these commands and possibly returning a response to the driver. And then the driver will be able to process that response and update some data structures, or even making this response available to user space. So let's review that state machine one more time. Here we have the finite state machine for Virtio stateful again, where we can see the states. We can see that the transitions between states happen by means of issuing ioctls. So the translation is going to be performed by the Virtio video kernel driver. And we can walk through a translation example, for instance. And here in this block diagram, I've chosen to walk through video C create or request buffs, which is a way how the guest user space is going to notify the kernel that it wants to allocate some memory for video data. So the guest user space program is unaware that it's being virtualized, and it's going to issue this ioctl against the kernel driver. Now the kernel driver is not just some device, it's a Virtio device, so it's going to receive this ioctl, and it's going to process this ioctl into some other Virtio specific command. And in this particular case, the command is Virtio video command resource create. It's going to place this command into the command queue, and then the device running on the host's hypervisor will notice that there's a command to be processed in the command queue, and it's going to talk to some black box, which I've denoted here as a question mark box. And this question mark box will possibly do some work, and it's possibly produce a response, and then this response is going to be piped all the way back into the guest Virtio video kernel driver, and the guest Virtio video kernel driver again will be given a chance to process this response and even make this response available to the guest user space by means of placing this response into some Virtio specific data structure. This is another example. So in this example, I've chosen to walk through what happens during query caps. So in this particular example, the guest kernel will probe the Virtio video device, and as the Virtio video kernel driver is booting up, the Virtio video kernel driver will be interested in knowing what kind of formats and what kind of resolutions are supported by the device. Because even though for Virtio video we have planned support for VP8, VP9, and H.264, that doesn't really mean that the underlying hardware will have support for all of these three. So the kernel driver is pretty much interested in knowing what video formats and what resolutions and so on and so forth the actual device will support. And in order to do so, it'll issue this Virtio video command query cap, and it'll place this command into the command queue, and then again the same thing is going to happen. The device will notice that there's a command in the command queue. It will dequeue the buffer with this command. It'll process this command somehow using some question mark component, which we're going to talk a whole lot more about in a few, and it'll come up with a response. It's going to place this response back into the command queue, and then lastly the Virtio video kernel driver running on the guest operating system will have a chance to process this response and update some internal data structures to reflect the kind of formats that are supported by the device. And I want to emphasize that the device in the virtual machine manager will be given a chance to reply asynchronously. It will not have to stop the world as it's the case with when you're emulating the device. And in particular, you will not have to incur into these costly VM exits all the time. And this is the example here of what the response for Virtio video command device query caps is. So you can see that here we have a struct which is going to be filled by the device, and then the kernel driver will be given a chance to process the data in this struct in order to update some internal data structures. And only for the sake of completeness, here are all the commands that can go on the queue. So on the command queue, you have query caps, you have a way to create a stream, destroy a stream, set and get stream parameters, drain and clear, and you also have some resource/memory related commands such as resource attach and resource queue. And here are all the events. For now, we have event resolution changed, which is when a decoder is processing the data and it notices that the resolution has changed midstream, so it issues this event in order to let the guest know, so that the guest may ask, for instance, for some new buffers for the new resolution. So let's recap a little bit. Here's the structure so far. We have a guest user space client program, which is going to be issuing ioctls, completely unaware that it's being virtualized, and it's going to be issuing ioctls just as if it was talking to some regular device. But in this case, the device is going to be a Virtio video device. So the kernel driver, the guest implementation, will be translating these ioctls, these incoming ioctls, into commands. It's going to be placing these commands into a command queue, and then the hypervisor, and in this particular case we're talking about Crosvm, so Crosvm will be dequeuing these commands. It will be processing these commands by virtue of talking with this question mark component, which we're going to dive into in a few, and then it's going to be placing the results of these commands back on the command queue, where the Virtio video kernel driver will be able to retrieve them. It'll also eventually be sending back some events, and also most importantly, it's going to be sending back some decoded frame data, and the kernel driver will be piping this data back to the guest user space, and then the guest user space will have issued the ioctls and gotten back the data, unaware that it was virtualized at all. Which brings us to the topic of the Crosvm hypervisor. So the Crosvm hypervisor is a virtual machine manager shipped with Chrome OS, and it's written in Rust, and the focus of Crosvm is on para-virtualized devices, such as the devices using the Virtio standard. And this is also because of the objectives that we talked about in some previous slide, which was to have seamless integration. So Virtio video really helps with that, because it really helps with improving throughput. So what is that shaded question mark box? Because for now, I think that right now it has become apparent that this question mark box is where the actual work is going to take place. So this brings us into the topic of the Crosvm backend. So back when I started, the only backend that was available was libVDA. So libVDA basically, it's a wrapper, and it uses the Chrome's GPU process to perform hardware-accelerated decoding and encoding. And it adds a dependency on Chrome. Now, there are a few issues with using libVDA here. The first issue is that libVDA does not work outside of Chromebook. So if anybody was trying to develop the Virtio video protocol using Crosvm, and that person didn't have a Chromebook, he would be completely out of luck, because there would be no way to decode the data. So, and it also adds a dependency on Chrome, so you arrive at the particular unfortunate situation where you have a virtual machine manager, such as Crosvm, depending on a web browser. So a person called Alex Kubo, which is one of the authors for the Virtio video protocol, worked on a backend that uses FFmpeg to decode frames. But then again, this adds a dependency on FFmpeg, which is a big C project using an unsafe language, which is again C. And also, by adding a dependency on FFmpeg, now one would have to somehow ship FFmpeg or maintain this dependency on this big program written in an unsafe language. So this brings us to the topic of the VA API backend. So VA API is a work in progress backend for Crosvm, and it can successfully decode VP8 data. And it uses the system's VA API driver to perform hardware accelerated decoding. And there's only one major difference that we have to talk now about, which is like VA API is a stateless backend. So it's a stateless API. So clearly some step has to take place, because as we talked about previously, the Virtio video kernel driver will be presenting itself as a stateful device. So how does this happen? And again, let's recap a little bit on the differences between stateful versus stateless interfaces. So here's the same block diagram that we had back at the start, only that now we've made a point of where this middle box used to read driver/firmware, and now I've made a point to have now a parser box. So it's important to note that inside of this firmware, somehow there's going to be a parser which is going to be parsing the bit stream in order to keep track of this decoding state. And on the stateless block diagram, I've also made a point where this first box used to read just guest user space. Now it reads user space parser and user space decoder, just so that we know that there's a parser component in there somehow, and this parser will usually be part of the client user space program, for instance, in this particular case, GStreamer. So clearly some translation has to take place in order for this to work. And this translation will be as following. The decoder must be implemented in the hypervisor. The parser must be implemented in the hypervisor. And the hypervisor now will be the piece that's going to be responsible for keeping track of the decoder state. And the hypervisor will relay this state to VA API at each and every decode operation. So let's talk a little bit about the VA API backend in particular. And this is the architecture of it all. So you can see here that we have a parser, a decoder, and a session all implemented in Rust and Crosvm. And these components, they will work together in order to call into a libVA wrapper crate. And we have a libVA wrapper crate because for those of you that have ever written Rust before, you might note that one of the unsafe superpowers is calling into functions defined into other programming languages. So any function that you call that's defined in another programming language will have to make use of a unsafe block. And we didn't want to have unsafe everywhere in Crosvm, so we chose to contain the unsafe calls into this wrapper crate. And then this wrapper crate will only expose a safe Rust API. And this wrapper crate will talk to some bindgen generator, and bindgen a Rust tool that generates FFIs. So it'll talk to this binding generated CFFI, and then by calling into these functions will call into the libva the libva library that's located on the host, and the library will call into the VA API driver. So for instance, if you're using Intel hardware, this is going to be Intel Media driver. If you're using AMD hardware, this is going to be Mesa, and the driver will then talk to GRM. And up until now, nobody really knows how to decode video data, but the GPU does know how to decode video data, because the GPU will have a decoder circuitry just for that. So the GPU will actually decode the frames, and it'll make the frames available, say, to GRM, and then the frames are going to be piped back all the way back until they arrive in Crosvm. And all these boxes, again, all these boxes here, they represent only the question mark box. So you can see that all these boxes, they represent the question mark box. So when the data arrives into Crosvm, then Crosvm will be able to push the data back into the Virtio video kernel driver, and then the Virtio video kernel driver will be able to somehow translate this data into something that the guest user space can understand. So now we should talk a little bit about each of the three constituent parts of the Crosvm backend implementation, starting with the parser. So the parser will be keeping track of the parsing state as needed, and it'll extract metadata from the headers in the bitstream, and it'll pass this metadata to the decoder. The decoder, in turn, will use this metadata in order to fill in some VA API structures, and it'll use the wrapper crate to ask for a decoder operation. And also, most importantly, it'll keep track of the decoder picture buffer, because as you will recall, now the hypervisor is going to be the piece of software that's responsible for keeping track of the decoding state. And lastly, the session. The session is it'll contain the device state for one playback session, and it'll also implement some Virtio video boilerplate, and by virtue of doing that, it'll also by proxy implement the virtual2 stateful finite state machine. And it'll also be the place where we will be able to share code between multiple codec backends, because if you look at this picture again, here we have the implementation for VP8, but if we add, and we do plan to add support for more codecs, if you add an implementation for VP9, you will also have to have a VP9 decoder implementation, an H264 decoder implementation, so on and so forth. So the idea is that this session is also a place where we can share code between all these implementations. And lastly, there's the libva wrapper crate, which will expose only a safe Rust API on top of the unsafe CFFI, and RAII will ensure that resources do not leak. It'll use bindgen to generate FFI bindings, and it will dynamically link to the system's libva. So in summary, let's recap a little bit. Virtio Video already powers many Chromebooks out there today, and it offers near native speeds when using Android applications. And Collabora is working with Chrome OS engineers on a way to bridge it to a fast and mature backend, which is VA, because VA is very well established and it's not going anywhere. It's already very well established. And this is a step forward in order to remove the dependency on libVDA from Crosvm. Also because we really want to make sure that people out there can develop Virtio Video using Crosvm without a Chromebook, and also because we don't want Crosvm to we don't want the Crosvm Virtual Machine Manager to depend on a web browser. So this makes Virtio Video more portable. Virtio Video, the protocol can be developed and run outside of Chromebooks using Crosvm, and this workflow will only become even more popular. This means that users can enjoy their Play Store video apps such as Netflix, YouTube, and they can even enjoy Android games that play video. And this is only one application of Virtio Video. There may be many more out there. So I want to end this presentation with one playful question, which is, what applications will you come up with using Virtio video? So anyways, my name is Daniel Almeida. Again, I hope this has made it a little bit more clear on how this entire process works and on how the virtual machine manager can actually decode data and make this data available to the guest operating system. Thank you very much.